So good afternoon, everybody. I'd like to welcome you, and especially our first speaker, Professor Martin Kusch, but also all of you. I'm very pleased to see so many people interested in this initiative, in the Ringvorlesung about foundations of physics. I will just spend a few introductory words. And first of all, I want to clarify the situation that I have almost nothing to do with this. Ringvorlesungen. The initiative for that and also the full organization was carried by a group of young scientists, physicists, Flavio Del Santo, Thomas Zauner, and a few other people, and I guess Flavio will say something about that. I was approached just to host this, and I was pleased to accept this. And also we supported this initiative by inviting and funding this initiative through the external speakers. So this Ringvorlesung will be devoted to the subject of scientific realism. It has this classical form of Ringvorlesung, and I'm very pleased about this idea. The proposed speakers will include eminent figures both in fields of physics and philosophy. We start with the philosophy. Well, we hope that it will be interesting not only for physicists but also from interested public, and will hopefully strengthen also the profile of University of Vienna as one of the, let's say, informal capitals of foundational questions in science. I must say that I'm very proud of this generation of young scientists who took this initiative and actually, in a sense, traditionally continue the long-standing tradition of epistemological schools of thoughts in Vienna, but maybe putting this in somewhat modern form aligned with the 21st century. So when I'm thinking about, great scientists and maybe more specific founders of, let's say, quantum theory, Niels Bohr, Albert Einstein, Erwin Schengen, Werner Heisenberg, Carl von Weizsäcker, or Wolfgang Pauli, then it cannot remain unnoticed that these people were not only great scientists, but they were also concerned with fundamental questions and questions of philosophical nature. And I think this is not an accident. I think if you want to make a big breakthrough, if you have a big idea in physics, this can't be done without really taking care about more conceptual issues of the theories and finally about philosophical questions. These all people that I mentioned were also not only interested in life, but they were engaged in many other problems, also ethical dilemma, especially during the Second World War. So they were a philosophical people. But of course, one should also try to find an exceptions in order to test this hypothesis of a necessity of the link between philosophy and physics. And of course, then first who came to my mind is Richard Feynman, who was especially critical towards importance of philosophy. In The Pleasures of Finding Things Out, he wrote about an event where he was reading Spinoza with his son, and they laughed a lot about that. And he ends the paragraph about that saying, you can take every one of Spinoza's proposition and take the contrary proposition and look at the world, and you can't tell which is right. So he openly denied importance of philosophy, but he was certainly a non-stereotypical scientist. He liked to play drums and hang out in the bars and so on. And I would like to think that at the end he was engaged in philosophy, even he was denying that. And even these thoughts about relevance of philosophy was a thought that has a philosophical impact. So, in a sense, I would like to believe that even if you have really strong opinion against philosophy, that you're actually trapped in the same line of thoughts. And I want to believe that what he wanted to tell us, that we should make a difference, and to make a difference between empty philosophizing and trying to understand the world from a philosophical point of view. And I think that, I hope that this ring formalism would also draw this line between these two things, and that we are on the right track. So, and I now give the words to Flavia to introduce the series of lectures.
Yeah, thanks very much for this very kind introduction. And yeah, basically Professor Bruckner anticipated, like really hit the nail on the head in the motivation that led us to organize this ring formalism. Yeah, we basically are a group. We started just randomly meeting for promoting interdisciplinarity and foundational questions in physics and in natural sciences. We called ourselves Naturwissenschaftscafé, mostly because I can barely pronounce it because I'm not obviously German speaker. And we started meeting on a regular basis, and we actually found that we all shared an uneasiness towards the way that the science is taught in most of the university courses. Basically, is completely devoid of any philosophical deep reasoning, and is most of the time you just scratch the surface of a very pragmatic approach without going to the philosophical questions that are, as Professor Bruckner historically pointed out, had a tremendous impact in the development of the most important theories of science. Therefore, we already organized several things, including maybe some of us that I know were participated already in the symposium of last year, still organized by us, Shut Up and Contemplate. And this is just a follow-up of that. So we thought that having a proper lecture where students can follow, take notes, and study properly and give and take an exam eventually will have a much stronger and long-lasting impact on their career and in their approach to science in general. So yeah, I just give you a few practical information for the course. So the course is structured, you all have, more or less all of us have a flyer in front of you, where there are the following dates. They are always on Thursdays, not all the weeks, but you find the dates. And what we did, as you can read in the short advertisement on the back, or you can read more in detail online, either on YouFind or on our website on Naturwissenschaftscafé. The aim of this Ringvorlesung is to give an overview of the problem of scientific realism within the domain of physics, in particular with the focus on quantum mechanics. Quantum mechanics has still several problems. I mean, there is a huge debate, which is lasting a century now, about the interpretations of quantum mechanics, the interpretation of wave function and the properties of quantum system, whether they own some kind of realism, some kind of reality per se. And what we did is following a recent nice essay by Adam Cabello, who actually ranked the different interpretations of quantum mechanics according to their degree of reality, of realism, either ontic or epistemic realism. And basically we picked the most still debated and active interpretations of quantum mechanics, and we asked one of the most eminent exponent of that current to come here to explain it to us. And therefore you will see now, because of organizational meeting, they are not really ordered as they should be, like Fuchs should be at the very end, but anyway. You will see that starting from next time, every time we will have a slightly different interpretation of quantum mechanics that cope in a different way with the reality that attributes to wave function and so on. The format of the lecture will be a 3-hour slot. That there will be 1 hour and a half or 2 hours of frontal lecture now. Then we will have a coffee break of 20 minutes in the small room behind here. And then there will be another hour of discussion. So we encourage people to not feel shy and to actually engage, especially today that Professor Kusch has come from the philosophy department. Many of us has very basic questions about realism that we just sometimes assume as straightforward as scientists, but there is a whole tradition that maybe is worth knowing. And at the end of the course, there will be a written exam with open questions that you maybe address me later if you want to know more about this. So without losing any more time, I give the word to Professor Kusch, and thank you very much for being here.
Right, well, thank you very much for coming. While we get the PowerPoints ready, let me say a few general things. So my assignment is a very simple and basic one. I will not give you an interpretation of quantum mechanics, but I'll give you a very first philosophy 101 introduction to scientific realism. So if you're already specialists in philosophy of science, then at least for the first hour you can rest your mind. Whereas I've designed the lecture such that people who have no prior knowledge of anything to do with scientific realism will understand the lecture. That's the first proviso. The second proviso is that as far as the sciences are concerned that I know about, I'm a philosopher of the social sciences, not a philosopher of the natural sciences or a philosopher, even less of a philosopher of physics. But I believe that there are certain general patterns in the different philosophies of the sciences that carry over. So therefore, I think even by being merely a philosopher of the social sciences, I can maybe tell you a thing or two about scientific realism. There is a handout going around. Don't be scared. This has very, very many slides on it. I won't get through all of those slides. I just thought it's good to give you those slides in case there is a specific point that comes up later that I jump ahead to in the question session, and then I can refer you to the respective slide. Okay, let's start. So I start with a position that I call classical scientific realism, and I think the best way to understand scientific realism is, first of all, of course, to know what the position is, but it's equally important to understand what the position is turning against. So therefore, in trying to explain to you scientific realism, I shall explain both the traditional ingredients of the scientific realist position and then also the best known opponent of scientific realism, namely Bas van Fraasen's constructive empiricism. So that's the main course that I will try to cover, classical scientific realism and its opponent. If there is time, and I hope there is, then I will subsequently turn to a more recently emerged form of scientific realism, namely structural scientific realism. And in this case, again, I hope to be able to both explain what the position is and to explain Bas van Fraasen's criticism of that position. Okay, so let's start. And just as I do in my other introductory philosophy lectures, let's begin by filling up our toolbox. We need a few basic philosophical concepts to be able to talk about scientific realism. Of course, the first very obvious term is a term in the philosophy of science, namely theoretical entities. Scientific theories often postulate entities that are not directly observable, and these theories are part of the apparatus but with the help of which scientists then make predictions or offer explanations. So such theoretical entities are black holes, genes, electrons, or electromagnetic radiation. That's the first element in our toolbox. Done. Now the second element of the toolbox, abduction or inference to the best explanation. Inference to the best explanation is an inductive form of inference, so it's not deductive but inductive, and it's one of the two main forms of induction. To explain it with a simple example, assume that we have a number of alternative hypotheses that are all empirically adequate, that all are true of the things that we can observe. And let's take a very, very simple example. Let's say we have the phenomenon that every day Mr. Jones sends red roses to Mrs. Smith. That's the phenomenon we are trying to understand. That's the phenomenon we want to have explained. Okay, now in order to explain it, we can try to come up with some possible hypotheses. Well, we might say Mr. Jones is in love with Mrs. Smith. Or we might say Mr. Jones hates Mrs. Smith, but has got too many roses lying around and is trying to get rid of them. Or another possible explanation is Mr. Jones mistakes Mrs. Smith for Mrs. Miller, and he's really in love with Mrs. Miller. Or Mr. Jones doesn't know at all what he's doing. So we have a number of explanation candidates. All of these things would, if true, would explain the phenomenon, and then inference to the best explanation is that we infer that that hypothesis that we best find explains the phenomenon, we infer that that hypothesis is true. So of those explanation candidates, under normal circumstances, I guess most of us would think the best explanation of the phenomenon that he sends the roses every day is that Mr. Jones is in love with Mrs. Smith. And therefore, if we apply inference to the best explanation, we infer that that explanation is true. Of course, this is a risky conclusion. It's an induction. An induction is always risky. Also, if you like, infer all of the ravens that in the past we have observed were black, therefore all ravens will always be black, is also a risky inductive inference. So inference to the best explanation is an inductive inference, therefore risky. We infer the truth of that hypothesis that we feel best explains the given phenomenon. Okay, it's important to note that inference to the best explanation is not deductively valid. So if you like say, Mr. Jones is in love with Mrs. Smith implies that Jones sends flowers to Smith, and then that's the first premise. Second premise, he sends flowers to Smith, therefore he loves Mrs. Smith. That would be, in deductive terms, a fallacy called inference to the fallacy of affirming the consequent. Okay. Second element of the toolbox, inference to the best explanation. Third element of the toolbox, the Quine-Duhem or Duhem-Quine thesis. So Pierre Duhem, of course, you all know, famous physicist, famous historian and philosopher of physics. One of his most celebrated famous theses is the following, quote, "An experiment in physics is unable to rule out an isolated hypothesis. It can only rule out a whole theoretical group." Basic idea is that the following naive view of scientific work is mistaken. The naive view would be something like, you have a hypothesis. The hypothesis implies that you should be able to observe a certain phenomenon. First premise. Second premise, the expected phenomenon doesn't in fact occur, it's not observed, and therefore you infer that the hypothesis is wrong. That's a naive view. Why is that a naive view? Well, because Duhem insists it's never a single thesis that we can test in science, it's only a whole theoretical group. Or in more formal terms, let's write H for hypothesis as part of a scientific theory, and let A stand for auxiliary hypothesis. Auxiliary hypotheses are not strictly part of our theory that we are trying to test, but concerns, for example, the working of our instruments. Because when we test a hypothesis, of course, we use instruments. And we make certain assumptions about the reliability about the instruments. Those are auxiliary hypotheses. So when we when we make a prediction in science and try to check whether a certain observation occurs, of course, you all know from your daily work, it's never an individual hypothesis that's tested by the whole group. And therefore, if the expected observation is not in fact made, you don't quite know exactly where the fault lies. The fault might lie with one of the hypotheses that make up the theory, or the fault might lie with one of the auxiliaries. So therefore, it's difficult to have decisive tests or refutations in science. I have an example here, but I jump over this. It's more important to explain to you the phenomenon of underdetermination that we can demonstrate with these observations of Duhem. So all I've done here in this simple-minded picture is we have the theory consisting of the three hypotheses. We also have a couple of auxiliaries. They imply together that a certain phenomenon should be observed, but then we try to observe it, we test it, and it turns out we don't observe it. So then we have different options. Let's just look at two of the options. One of the options on the left would be to say, well, the fault doesn't lie with our theories. With our theory, the fault lies with one of our auxiliaries. One option, one way we can go. Another way we can go is to say, no, the fault doesn't lie with the auxiliaries, the fault lies with one of the hypotheses. Okay, so the difficulty is, what do we do in such a situation where we could go more than one way? What should we conclude about the theory and about the truth of the theory when we are in such situations of underdetermination? What we have here is a case of underdetermination. The one observation in this simplified scenario, that the one observation didn't materialize, that we were unable to make the observation that the theory predicted we would make, leaves it open how we proceed from here. We either can correct the auxiliary or we can correct the hypothesis. Both of those ways of proceeding are empirically adequate. Both can explain the phenomena. So what should we do in such cases? Well, one conclusion one might draw, and that some philosophers are inclined to draw, is to say, well, under those circumstances, we should simply suspend judgment. We shouldn't judge. Okay, now, Duhem, already quite an important radical view, but van Quine, very important American philosopher of the second half of the 20th century, pushed the Duhemian ideas one step further. The key claim, compared with Duhem, is that he says the unit of empirical significance is the whole of science. What does that mean? Well, one thing that might mean, or one way to illustrate what he might mean, is to look at this structure, a hemispheric bowl as model of human knowledge, where you have these different elements of this overall structure. Think of every point where two lines cross here as a belief, if you like, or as a theory, if you like. The idea is that all of our knowledge is one big structure. Our different theories, from geography to quantum mechanics, from biology to the social sciences, Quine says, are all part of one big holistic whole. Therefore, when a given observation doesn't occur, it isn't just about two or three hypotheses that you might have to change, the way in which Duhem was presenting it, or a few auxiliaries. But as Quine sees it, in our experiments, it's always the whole of our knowledge that is being tested. So that was the picture I gave you for Duhem. The Quinean version is to say it's the hypothesis, it's the auxiliaries, and it's all the rest of science that is involved. And of course, there are some examples of this. I mean, think, for example, of the case that sometimes empirical results in science can force you to think differently about certain tools in mathematics. Or, for example, certain results in astronomy force people to change their views about the human perceptual system. So that was a case when observations that weren't reliable in astronomy led people to develop theories in the theory of perception. Those are examples that Quine and others give in this vein to emphasize the holistic character of our knowledge, that you can never be sure when a certain observation doesn't occur that the fault has to lie at one specific place. It can lie in quite surprising places. Okay, we got under determination, we got Duhem and Quine. Now we need to do a little bit of philosophical semantics, philosophy of language. And here the first distinction that we need is the distinction between truth values and truth conditions. The truth value is simply a value indicating the degree to which a sentence or proposition is true. Normally the truth values are just true or false, but of course you could have more complicated, you could have 3 values or 4 values, or you could have 1 for true, 0 for false, and then anything in between for different grades of truth. So that's the truth value, the degree to which a given sentence or proposition is true. The truth condition is the condition under which a sentence or proposition is or would be true. Let me give you an example of how this works, where I also make a distinction clear that I didn't explicitly highlight here, namely the distinction between sentence and proposition. So, first of all, take 2 sentences like Uoho on Vichria, Finnish sentence, and the Spanish sentence La hierba es verde. Those are 2 sentences of 2 different languages. But these 2 declarative sentences express the same thought, or, as philosophers like to say, express the same proposition. For our purposes, we can simply say thoughts, proposition, roughly the same thing. There are other reasons for which it's very important not to say that. For our purposes, that's good enough. Okay, so declarative sentences express propositions. They have content, and we use the propositions in order to be able to say which declarative sentences belong together. Because the sentences, Uoho on Vichria, La hierba es verde, grass is green, grass is grün, those are all declarative sentences, all expressing the same thought. Namely, we can use the German language to pick out this thought, grass is grün. Okay, so we have sentences. Sentences express thoughts or propositions, and then propositions have truth conditions. The conditions under which that sentence or proposition is true. And in this case, the truth condition is obvious. The sentence, Uoho on Vichria, is true if and only if grass is green. Okay? Sentence, propositions, truth values, truth conditions. Truth conditions can be expressed in 2 different ways, or you can have 2 different views about truth conditions. One way to think about truth conditions is to think of them as something objective. When you think of truth conditions as something objective, then you make no reference to a person for whom this is a truth. Then you will say the truth condition of Schnee ist weiß is that snow is white. You can also express truth conditions if you have a different view about truth. You might be inclined to express truth conditions differently and express truth conditions in a more subjective form by saying, Schnee ist weiß, the truth condition is that snow seems white. Well, this expression seems, of course, refers to someone for whom it seems that way. So that would be to give a subjective truth condition, a truth condition referring to a human cognizer. Okay, we also need a distinction between 2 types of sentences. A sentence can be assertoric, or a sentence might not be assertoric. A sentence is assertoric when it claims something about the world and when it expresses a proposition. So, for example, snow is white is an assertoric sentence, it's an assertion. But of course, there are other sentences or other expressions that are not assertoric. As when I say good afternoon or good evening, that does not make a claim about the world. I mean, you might say it implies a claim about the world, namely that it is afternoon, but the expression itself is not assertoric. The tricky bit in philosophy, when philosophers analyze language, is of course not the snow is white case, or it's not the good morning or good afternoon case, but that there are certain sentences that look like they are assertoric, but they aren't really assertoric on the analysis of some philosophers. So take, for example, moral assertions. Take an assertions like, it's morally bad to tell lies. Does that express a fact? Is it assertoric? Does it claim something definite about the world? Well, depends where your philosophical theory takes you. Some people are inclined to say that. Other people are inclined to say that no, moral claims are not assertoric. They express a certain attitude. That the right semantics of moral language is a language that focuses on the emotions that are being expressed in saying such a moral claim. So if one has to translate it's morally bad to tell lies on that interpretation, it means something like telling lies, boo, being honest, hooray. So those are not assertoric sentences, but those are expressions. So, almost finished. We also need to know something about reduction. Very key term when philosophers think about science. It's common to distinguish between two forms of reduction, namely reduction as incorporation and reduction as elimination. Reduction as incorporation, a good example of which is when physicists came to recognize that heat is molecular motion. By doing so, one could better say what heat actually is. One could appropriately incorporate heat into more fundamental physical theory. So that was reduction as incorporation. One pointed to the proper place heat has in physical theory. It didn't mean that there is no heat. It was rather, we now know what heat really is. From that reduction as incorporation, it's important to distinguish reduction qua elimination. So, for example, take witches. Why don't we think that witches exist? Well, we tend to think that there is no basic important scientific theory such that we can say witches are really that. And then we have a category in accepted, let's say, psychological or psychiatric classification and can say, oh, this is what witches really are. That we can't do. So we can't match witches onto any accepted category. So therefore we think witches don't exist. There are some psychohistorians, historians of psychology and psychiatry, who claim that if one looks at the symptoms that were often attributed to witches, most witches were actually psychotic. Well, I'm not sure that that's true, but assume that were true. Well, then we could incorporate witches into an accepted scientific theory, and we would be on the left-hand side. But failing that, in this case, for witches, we have reduction as elimination. The difficult bit is that reduction is sometimes used just for the incorporation bit, and sometimes reduction is used for both incorporation and elimination. But as long as you recognize this, you're clear. Final element of the toolbox, you would see that afterwards goes much faster by having these things in our toolbox, so I have to put them there. The final thing that we need in our toolbox is a distinction between two kinds of skepticism. Epistemological skepticism and ontological skepticism. If you are an ontological skeptic, then you deny the existence of a certain entity. So if, say, you're an ontological skeptic about God, then you will say there is no God, period. If you're an epistemological skepticism, then you're not making a claim about existence, but you're making a claim about whether we can have epistemic justification in a certain realm. And you might, for example, say, look, we can't have knowledge about God because we can't really have good epistemic grounds for believing in him. That doesn't prevent you from being a religious believer. You will just say knowledge and epistemic justification in that area isn't possible. Then you're a skeptic concerning the possibility of having an epistemic justification for something. That need not take you as far as denying the existence. Okay, so it's important to distinguish between ontological skepticism, denying the existence of a certain entity, and epistemological skepticism, denying the possibility of having an epistemic justification for something. Okay, toolbox is full. Now we can turn to our real topic, and we can use the tools that we have introduced to present the position in the most, hopefully the most crisp and clear way. Sorry, jumped ahead a bit. Okay, so scientific realism. Very briefly put, scientific realism is the view that claims it's rational to believe in the existence of those unobservable entities that are postulated by our best scientific theories. That's in one sentence. But we will go over this from different angles. So we started off with theoretical entities, and scientific realism says you are entitled to believe in the existence of those entities that are postulated by our best scientific theories, even when those entities are not observable. That's the position. But if one looks a bit more carefully, a bit more closely, it turns out that scientific realism is actually a combination of three different views that are well worth keeping apart. First of all, scientific realism has a metaphysical component. Metaphysics is about, roughly speaking, what there is in the most general terms. And scientific realism is committed to a form of metaphysical realism, to a realism about what kind of entities exist. And the claim is the types of entities science talks about really do exist, even when they are not observable. And also the existence of these types of entities is independent of our knowledge and our language. They don't exist in the sense in which chairs exist. We make chairs. The claim is rather they exist and they would exist even if we weren't around. Okay, that's the metaphysical component of scientific realism. Then comes the semantic component of scientific realism that has two elements. First of all, scientific claims about theoretical entities are not reducible and they are genuinely assertoric. Now we can use both reduction and assertoric. So scientific claims about theoretical entities are not reducible. So when we talk about electrons, that's not just a complicated way to talk about certain things that we can see in our measurement instruments. When we talk about electrons, we really talk about those things as being somewhat independent of us. Talk about electrons is not reducible to talk about something else. That's the element of it's not reducible. And secondly, they are genuinely assertoric. So when scientists talk about electrons, they really mean to make a claim about those entities out there in the world. They are assertoric. They're not like good morning and not like a certain way of doing physics. Hooray. No, that's not what talk about electrons means. That's the first element. And the second element is basically a version of the correspondence theory of truth. The truth conditions of scientific claims about theoretical entities are objective. They are objective, not like what seems like to some people. The truth conditions are objective and determine the truth or falsity of these claims depending on how things stand in the world. So what makes scientific claims true, regardless whether they are about observables or unobservables, is how things stand in the world. Okay, and then we come to the third element, which is the epistemological element, and it says that it is possible to know the truth about theoretical entities. So now we talk about knowledge. What can we know? And it says it's possible to know the truth about theoretical entities. And indeed, we know some of those truths already, and some of the terms of scientific theories successfully refer to theoretical entities. Well, that last element actually should go, I just noticed, should go under the semantic conditions. So the claim is that the terms that we use in science, a term like electron, actually points to, refers to real things out there in the world. Okay, so now we know what the position is. Now we need to know, well, why should we accept it? It's one thing in philosophy, and it's often difficult enough in philosophy to state a position with sufficient clarity. But even if one has, with lots of luck and hard labor, achieved that, there still is the further task of trying to give good arguments for it. Well, fortunately, as far as scientific realism is concerned, there is a certain master argument that almost all defenders of scientific realism in some form or other have defended. Likewise, there's also one central counter-argument. And so if we look at those two arguments, we have covered quite a bit of the argumentative toing and froing in that area. So first then, the master argument for scientific realism, and this is where our inference to the best explanation, Mr. Smith, Mrs. Jones, and the Roses are coming back. Okay, so there are two ways to use inference to the best explanation to defend scientific realism. Let me repeat this. There are two ways to use inference to the best explanation in order to defend scientific realism. There is a local use of inference to the best explanation, and there is a global use of inference to the best explanation. But in both cases, the inference we are supposed to draw is the same, namely that it's well justified for us to believe in the theoretical entities postulated by our best scientific theories. So let's first look at the local use of inference to the best explanation, and therefore the local defense of scientific realism. Well, it goes like this. Take an example of a really successful piece of science. Take, for example, the theory of molecular structure. And look what all this theory can do. It's fantastic. It can predict and explain an enormously wide range of phenomena. And because the theory of molecular structure can explain all these things and predict so many features, therefore it's only rational to assume that the sort of entities that are involved in that theory of molecular structure, starting with atoms and electrons, really do exist. So it's local, the defense of scientific realism, because we pick one chunk of scientific theorizing and convince ourselves, or so the scientific realist wants to convince us, that by looking at this successful piece of science, it should be blatantly obvious that the kind of entities that those theories postulate really do exist. So, to accept the rationality of science in light of such examples, the local use of inference of the best explanation says, is to accept the rationality of that inference of the best explanation. The best explanation, let me put it differently, the best explanation for why the theory of molecular structure is so successful is that the entities that are postulated by that theory actually do exist. That's the argument. What's the best explanation for the success, predictably, and with respect to explanations of the theory of molecular structure? Answer, so the scientific realist, the best explanation is that those entities that are postulated by that theory actually do exist. Now let's turn from the local use to the global use of inference of the best explanation, or the global defense of scientific realism. This goes back to the famous American philosopher Hilary Putnam, though strictly speaking he wasn't the first to come up with this argument, but it's generally attributed to him. So let's keep with that tradition. And that's the famous no miracles argument. So, which very briefly put goes like this, quote, the positive argument for scientific realism is that it is the only philosophy that doesn't make the success of science a miracle. So now we don't look at one particular theory. Now Putnam invites us to look at all of science. And just like initially we made our list of things, why does Mr. Jones send flower to Mrs. Smith? Now we try to make a list for how come science is so successful. Well, one explanation for why science is so successful is the hypothesis that Putnam proposes, namely that the entities postulated in our best scientific theories actually do exist. That's one explanation for why the theories are successful. We might have some other explanations. For example, Putnam considers one alternative. The alternative is, well, maybe the success of science is just a miracle. So now we have two. So we got either it's a miracle that science is so successful, or the alternative is that science is so successful because the entities postulated by our best scientific theories actually do exist. Well, says Putnam, it's clear what the best explanation is, isn't it? Namely that the entities that our best scientific theories postulate actually do exist. So now, note this is not a local defense. We're not talking about the theory of molecular structure. We're talking about science as a whole and try to think up possible explanations for why science is successful. And then, as inference of the best explanation urges us to do, we pick the one that best explains it. When we do this as philosophers, we, as Richard Boyd points out, we kind of treat philosophy itself as an empirical science. Normally in empirical science, one has different hypotheses that would explain a given phenomenon, and then we infer the truth of that hypothesis that best explains it. When you're doing what Putnam is urging us to do, we are now treating philosophy as like an empirical science about science. And we step back from all of science and ask ourselves, what explains the success of science? And then the argument proceeds as Putnam suggests. So that's the argument for scientific realism. Now let's look at the main argument against scientific realism. And that argument goes back to the American philosopher Larry Lorden, who presented it in 1981. And just like the no miracles argument, so also this argument has been written to death. I mean, I don't know how many hundreds of papers have been written discussing different versions of the argument, different ways to criticize it, different ways to defend it, and so on. So let's take that argument step by step. It takes a bit longer to take this argument in than Putnam's argument. Okay, so this is called the pessimistic meta-induction. It's called meta-induction because it's an induction about the inductions done by science. Science is, of course, inductive, and now we are trying to make an induction about the attempts of scientists to come up with successful inductive inferences. Okay, so first element, or first step of the argument. In the past, there have been many empirically successful scientific theories that were later abandoned. Their theoretical concepts their theoretical terms do not, by our standards today, refer to real entities. That's the first step. So in the past, we have had theories that were predictively successful, that also were explanatory. They helped us to understand why certain things were happening. And yet later, we gave up those theories, at least in big chunks of those theories, and we concluded that the theoretical terms referring to unobservables in those theories do not, in fact, refer to anything. Certainly not refer to those theoretical entities that those theories were assuming. Well, what are some examples of this? Lorden gives a long list. Here are some elements. The crystal spheres of medieval astronomy, the humoral theory in medicine, the phlogiston theory in chemistry, the caloric theory of heat, the vibration theory of heat, the theory of vital powers in physiology, the theory of electromagnetic ether, the theory of optical ether, the theory of spontaneous generations, and others. All of those are examples of theories that were predictively successful. So they kind of fulfilled the requirement of what makes a scientific theory a good scientific theory. They were successful theories. And yet later we came to conclude that those theories are not ultimately correct, and therefore we also assume that the essential theoretical entities postulated by those theories, like crystal spheres, humors, phlogiston, and so on, caloric, that those entities do not, in fact, exist. So that's step one of the argument. Step two of the argument is that we have good inductive grounds for assuming that in the future our theories will be replaced by other new theories. And the inductive ground for this is simply, this is the way it's always been in the past, and why should it be different in the future? In light of the future theories, it will turn out that some of the central theoretical entities or concepts of our best theories do not refer to existing entities. So just like theories of the past that were predictably successful were later abandoned, and we decided that their theoretical entities do not in fact refer, so it will also happen to our scientific theories, that later we will come to conclude that the theoretical entities that are central to our scientific theories will also be given up. So, what are we supposed to conclude from this? Yeah, I guess it's obvious. This is an argument against scientific realism. We have good reasons not to believe in the existence of entities postulated by our best theories. Right? So, the numericals argument went from, look, our theories are so predictively successful that surely we should assume the existence of those theoretical entities that are postulated by those theories. Surely. Theories usually stump the table or the table. So, surely we should do that. And the pessimistic meta-induction says, well, they might have said very much the same thing in the 17th century. They might have said very much the same thing in the 18th century, and many versions of theories in the 19th century. So why should our theories be so principally different from theories in the past? Well, but if our theories are not principally different from theories in the past, then presumably our theories and our theoretical entities will meet the same fate as theoretical entities and theories of the past. They will be given up sooner or later. So that's the pessimistic meta-induction. The pessimism is that whenever we find a certain group of theoretical entities utterly compelling, well, history tells us that that's just how it appears to a given historical period. Okay, so that's that argument. So we have now seen what the position is of scientific realism. We have looked at the main argument for scientific realism, and we have looked at the main argument against scientific realism. The next step is to understand what are some alternatives to scientific realism, and in particular, I will home in on the alternative of Bas van Fraassen and the position he calls constructive empiricism.
Could we have some lights?
Some lights? You mean you want to see me, or what do you want? Oh, these lights. I don't know how to turn those on. Does someone know how to turn the lights on? This one.
Thank you.
No, the other one. Switch off the first one, then
Cable the others.
You want it on?
No. Perfect. It's fine.
Like this? Yeah, I don't mind. Okay. Well, you can still see the slides. So okay, good.
Keine Scheinwerfer extra.
Die Scheinwerfer kann man jetzt hören. Nach der Zeit ist das schon
Okay, well, I'm fine like this. Are you fine like this? Okay, good. So, alternative to scientific realism. And the easiest way to home in on the alternatives is to go back to our main ingredients of scientific realism and then see whether there are positions that selectively deny elements of those different components that make up the core of scientific realism. So we had this first element, the metaphysical element, types of entities science talks about really do exist, and the existence of those entities is independent of our knowledge and our language. Well, there are at least two ways to deny this, at least two. You might be an idealist. You might thereby deny two. You might say, well, tables and chairs are real, but they're real only as some kind of mental entity. Or you might be a Berkeleyan idealist to say that, well, all the existence means things are in the mind of God. And we can participate in that existence insofar as God infuses us with those ideas. But then you don't really think that the existence of entities is independent of our and God's knowledge and language. Or you might be an ontological skeptic and say, no, I don't believe that any of these objects exist. We should be skeptical about all sorts of objects, including the objects of science. You might, of course, be denying an element of the semantic assumptions. So the essential semantic assumptions was that scientific claims about theoretical entities are not reducible. Well, you might, for example, say that no, claims about certain key theoretical entities are in fact reducible. You might say, no, electron talk really is nothing but a very convoluted, complex talk about certain measurement results. And talk of electrons can be reduced to talk about certain types of measurement results. Well, we might call that position semantic instrumentalism, and it clearly denies a key feature of scientific realism. Now, the position that I said I'm most interested in, and that is the main alternative in contemporary debates about scientific realism, is the position called constructive empiricism. As far as the metaphysics is concerned, it doesn't deny that the types of entities science talks about really do exist. It says, well, maybe we should be agnostic about it. We shouldn't deny it, but we shouldn't believe it either. And the position denies, however, the epistemic assumptions that it is possible to know the truth about unobservable theoretical entities. It denies that key feature, and that, of course, dramatically sets it apart from scientific realism. On the other hand, constructive empiricism takes no exception to the semantic assumptions, but accepts them as such. If this sounds unduly theoretical and abstract, let me make this more concrete by homing in more on the nitty-gritty of what Bas van Fraasen actually says. So that is the man, and his great hobby is mountain climbing, rock climbing. He's still doing this at this age, amazing guy. Let's first see how van Fraasen draws the distinction between scientific realism and constructive empiricism. It's very useful to do, to follow him here, because this is a case when, like, the critic gives the position the most crisp formulation. So, like, even defenders of scientific realism and thereby opponents of van Fraasen think that he has very clearly set apart what scientific realism and constructive empiricism actually is. So here's his definition of scientific realism. According to scientific realism, science aims to give us, in its theories, a literally true story of what the world is like, and acceptance of a scientific theory involves the belief that it is true. I've highlighted a few key terms here. First of all, aims. So he says scientific realism is a claim about the aims of science. He's not talking about the motivation of individual scientists. He talks about the aims of science, first. Secondly, for scientific realism, science ultimately, in the end, gives us a literally true story about what the world is like. That's the second key element. The third key element is that scientific realism is a specific theory about what it means to accept a scientific theory. What does it mean to accept a scientific theory? Answer: to accept a scientific theory is to believe that it is true, and true both concerning its observable parts and concerning the claims it makes about the unobservables. Here's a picture that I use in my undergraduate lectures to make that clear. So the ball is a scientific theory. Above the line you have sentences about observable entities. Below the line you have sentences about non-observables, about theoretical entities. Okay, so scientific theory consists of those two parts. Claims about observables, claims about unobservables. Now, the aim of science for the scientific realist is to make both elements true. We want that our scientific theory is true as far as the observable is concerned. We want that scientific theories describe what we can observe correctly. And we want that our scientific theories make claims about the unobservables that are true. So for the scientific theories, the aim of science is to have theories which kind of have both of those components, both true concerning the observables and true concerning the unobservables. Okay, now let's look by contrast at the constructive empiricist position. For the constructive empiricist, as van Fraassen formulates it, science aims to give us theories that are empirically adequate, and acceptance of a theory involves a belief only that it is empirically adequate. Empirical adequacy, what is empirical adequacy? A theory is empirically adequate if what it says about observable things and events in the world is true. Let's look at the picture so that the contrast becomes clear. So according to constructive empiricism, the goal of science is to have a theory that as a whole is empirically adequate. And what does it mean that the theory as a whole is empirically adequate? That means that what the theory says and predicts about the observable things is true. Right? The important contrast is between those two balls. For the scientific realist, the aim of science is to have theories which are true, meaning true both concerning the observables and concerning the unobservables. And for the constructive empiricist, the goal of science is to have theories that are empirically adequate. We want to make sure the theory is true as concerns those features that the theory predicts and that we can observe, but we cannot make it so that our theory is true about the unobservables. We just have no way of finding out. So therefore, we can talk about electrons, we can talk about the unobservables. It's not as if the constructive empiricist says you're not allowed to talk about those theoretical entities. Yes, you're allowed to talk about them, but you're not allowed the attitudes of believing that what your theory says about them is literally true. You are allowed to use them as part of the machinery that enables you to make predictions, but you are not allowed to assume that they really exist. This is important. This is the way in which van Fraassen is often misunderstood. People tend to misunderstand the position as thinking van Fraassen wants to change the practice of scientists. No. Van Fraassen is one of those people who think that philosophy leaves things as they are. We're just trying to understand them better. Right, so the point is you can do exactly the science you did before, but you have to change your cognitive attitude towards the unobservable entities. You can operate them within your theory the way you have always done, but do not assume that your claims about the unobservables are literally true. What should be literally true, and what every good scientific theory should aim for, is that your theory is true concerning its predictions, concerning the things that you can actually observe. That's the aim of science, to be better able to make predictions and explain phenomena. But the aim of science, von Phrasen thinks, is not to make ever better claims about things that we cannot observe. That, for von Phrasen, is a misunderstanding. Let's have the questions after the break. I understand that many of you will object to this, that, and the other, but let's leave the discussion until we've got a little bit more detail. So, in von Phrasen's theory, there is one term that's very essential, and that's the term observable. What is observable? For von Phrasen, something is observable if it is observable without an instrument. Observable for von Phrasen means observable without an instrument. So take an example. Take a bubble chamber. Von Phrasen would say we are not observing electrons in the bubble chamber. What we are observing is certain traces of bubbles. That's what we actually observe. And then we infer that these traces of bubbles are caused by electrons. And then, of course, the scientific realist will say, well, since electrons so nicely explain the traces, therefore I assume electrons exist. Von Phrasen will say, you can talk this way, but don't think that way. The way you should think is that what you actually observe is the traces of the bubbles. And then to go from there to saying they are electrons is not an observation, it's an inference. And that's an inference to the best explanation. And inference to the best explanations are risky. Well, what about the moons of Jupiter? That's the essential. Another example that von Phrasen mentions. Are the moons of Jupiter observable? Yes, says von Phrasen. The moons of Jupiter are observable. Why are the moons of Jupiter observable? Surely we also see the moons of Jupiter only with the help of telescopes. Yes, says von Phrasen, but our best scientific theory tells us that if we put humans in a spaceship and fly them past Jupiter, they will be able to see the moons of Jupiter without an instrument. So our scientific theories tell us that the moons of Jupiter are observable for creatures like us, provided we are brought in the right kind of position. But the electrons, there is no scientific theory which tells us that there is a way of making us fly past the electrons, such that we will be able to observe the electrons without an instrument. Okay, final point, and then, as far as I'm concerned, we could have a break. As you will have seen, for the scientific realists, inference to the best explanation is absolutely crucial. Inference to the best explanation is what is driving the arguments of the scientific realist. And of course, the constructive empiricist, since he does not want to draw the conclusions the scientific realist wants to draw, of course will disagree, therefore, over what one can do with inference to the best explanation. And von Phrasen is skeptical with respect to the uses the scientific realist wants to make of inference to the best explanation. Well, here are two very general arguments that von Phrasen sometimes uses to make us feel uncomfortable about the inference to the best explanation that scientific realists want to do. Well, here's the first argument. Assume that we have empirical observations And we have 3 different theories that explain and predict those empirical observations. So they're all empirically adequate. And now we ask ourselves, well, which one of those should we actually choose? Well, if you apply inference to the best explanation, you might say, well, there's one of the 3 that actually explains it better than the other 2. Just like the hypothesis about Mr. Jones loves Mrs. Smith explains the sending of flowers better than that he hates Mrs. Smith. So the scientific realist will say, yeah, theory 2 explains it better than the other 2. Therefore, inference to the best explanation, that theory is true. Well, says von Fraasen, but we need to remember this idea about underdetermination, those ideas that we learned from Duhem and Quine, that we often in science have the situation where we have different theories that can explain the same phenomena, even though the theories are different. So surely there can also be, for this theory T2 that here explains best, there may be an alternative to this theory, a theory that we haven't yet hit upon, but that's certainly possible, and often in the history of science we hit upon theories later that at first we didn't consider as appropriate rivals to our theories. And it may be that this theory is empirically equivalent to T2, but it is incompatible with T2. Just like when I gave you this scenario in the Duhem case, that in the one case we modify one of the hypotheses, and in another case we modify one of the auxiliaries. Both theories are empirically adequate, and then how do we choose between those 2? Underdetermination. So surely there may be cases where there is another theory that we hadn't thought of yet, an alternative to T2, such that it's underdetermined in light of our empirical evidence, whether we should use T2 or this theory T4. But if that's possible, then we shouldn't choose T2 as being true. Here's another example, another argument, which is called the best of a bad lot, which is to say, well, maybe we have theories T1, T2, T3, and of those 3 theories, T2 best explains the observations. But it could very well be that all of the theories that we choose between are actually bad theories, and to pick the best theory of a bad lot is not going to be very good if you want to infer to the truth of that theory. I mean, assume, for example, that, go back to the case where Mr. Jones sends flowers to Mrs. Smith. Assume that we had noticed earlier that Mr. Jones, in fact, has a big flower transportation company that picks up flowers from Holland and then drives around Austria to deliver the flowers. Well, maybe we hadn't considered that very important feature of Mr. Jones. So Mr. Jones sends flowers to Mrs. Smith every day, but lo and behold, none of us had thought about the possibility that it may be because he's delivering it to her flower shop. Well, once that possibility is on the cards, then of course we realize that our previous whole way of thinking about it was rather confused. Well, if that sounds contrived, remember that in the history of science, it over and over happens that we have a bad lot that we choose between, and suddenly a new option emerges, and that completely changes the framework within which we make our decisions between the theories. Okay, so here's where the philosophy of science, Scientific Realism 101 lecture ends, and I could go on to explain structural scientific realism and its opponent, but I'm also happy to have a break here and then go on, or I'm happy to open for discussion and we have discussion. I'm happy with any of those options. That wasn't an option. So thank you very much, but that still leaves the question what we do next.
So you mean that you're going to talk more after the break, or after the break we're going to make the questions?
I'm happy with anything you want to do. We can start the discussion now, I can go on, we can have the coffee break, and then I go on, we can have the coffee break, and then we discuss what we have done so far.
Maybe discuss it and afterwards break.
Discuss first, break, and then go on. Any objections? Okay, then discuss. The gentleman over there had a question, so now.
What's clarified on your next slide?
Good. Yes.
So I was thinking about this difference between observing with the eye the moons of Jupiter and using an instrument. Because the spaceship is also sort of an instrument, right? You use it and you trust it actually flies there and show you the
Yes, that's the standard unease about that case. But Van Frazen says, look, I'm going with what science tells us about the human body as a measurement instrument. The human body can be thought of as a measurement instrument. And what science tells us is that if we put that measurement instrument in a certain orbit around Jupiter, then that measurement instrument, without the help of anything in between, will be able to see, to register, to see that there are the moons of Jupiter. It's true that, of course, a certain instrument took you there, but that shouldn't be such a big issue, because you might also say that my sister is observable, but it's only observable if you get on the train to Cologne. You can't observe her right from here. You could still say that she's observable, even though you need a certain machine to get there. But that's different with the electrons, because our best theory about the human organism tells us that there is no way to turn the human organism into something so small that they can be eye to eye with an electron.
At hope. But if a certain astronaut sees the moon of Jupiter, and how should I believe it? I am informed also by television, by instruments that he has seen.
Right, but that's not quite the same thing. There we are now talking about questions to do with under what circumstances is it rational to trust the report of another human being. There are interesting epistemological questions to be raised about that, but that, for all intents and purposes, we bracket that, because you might say that applies to almost any scientific phenomenon. That one is dependent on the testimony of other sources. The question was whether it is observable to a human, not to any particular human, because you might say that the scientist or the astronaut who flies by Jupiter is a member of our epistemic community. And then, of course, one element of the epistemic community can report something to another element of the epistemic community. But that's different from the electrons, because people have, like Paul Churchton have said, well, couldn't it be that, like, eventually humans develop such that they have electron microscopes for eyes? And then, of course, wouldn't they then see the electrons eye to eye? Yes, says Van Frazen, they would. But as things stand, they are not members of our epistemic community. So these scientific cases, these science fiction cases, don't really define our scientific community. Okay, there was someone else? Yeah?
So the objection of Van Frazen to the usage of instruments in order to extract some kind of observations was that the instrument has to do with our theories, and they measure that the instrument measures something that comes actually through our theories, or what was the objection exactly?
Well, I mean, the main thing is to simply ask yourself, what is it that we are observing? I mean, let's take something a bit more basic. Let's take a microscope. What do we actually observe when we use a microscope? Well, we observe a certain image on the lens. That's what we actually observe. That we then say, oh, and what we actually see here is a certain cell or something. That's an inference. Van Frazen urges us to recognize that we should be aware of what it is that we actually see and what are the inferences that we draw on the basis of what we are seeing. I mean, yeah, I leave it there. There are lots of further tricky issues involved there. I think there was a question here and then there and then here.
I was actually kind of surprised that Van Frazen talks about already the tracks of bubbles.
That he talks what?
What he sees are tracks of bubbles.
Are traces of bubbles, yeah.
Yeah, that takes a lot of knowledge already, a lot of experience. I mean, if I show this to somebody off the street, he would probably not say these are traces of bubbles.
Yeah, that's fine. But when Van Frazen says something is observable, it doesn't have to mean it's observable to any member of the human species. It might very well be that it's a member of the human species with some further training. But it can't be that much further training that the inferences become part of what you see. So you can't say, well, I've been so well trained in physics, I see the electrons there. No, that Van Frazen would say you cannot say. You need certain experience to pick out that there are traces of bubbles that you need some experience for. But it's not like you're going beyond the observable. But of course, I think your unease is justified to the extent that it may well be that Van Frazen assumes a more clear-cut boundary there than is actually plausible. I'm completely open to that. Sorry, because the gentleman back there.
Yes. So I mean, actually, what makes the human so special? I mean, this is kind of like why would something is true or like adequate if I can observe it this way? What makes I can see the moon because there are photons bouncing off there. Aren't photons some kind of instrument? The same is with the eyes. And I think actually what you said just now was very interesting when you said, oh, it doesn't have to be any person in the world. So the blind person couldn't say something is observable. I mean, what does a blind person do? And then, like, in all of these theories, kind of very interesting that you never said something about, like, intersubjective things, because, like, all of this happens in society, right? So, like, it is a very important part of the whole concept that we can communicate. And then to see what is true there, like, what means truth, I mean, in the whole concept is very non-clear. Right?
Okay. Yeah, there were several issues. First of all, it is true that both in standard scientific realism and in Van Frazen's view of science, the social nature of science does not play a very significant role. Those things are seen as orthogonal. There are certain debates you might have about the social nature of science, and there are certain debates you might have about scientific realism versus constructive empiricism. It's standardly assumed in those philosophical debates that those are orthogonal. As it happens, I personally disagree with that, and much of my work is about the social nature of science, and I think it's important also when one considers these sorts of questions. So that's the first thing. In order to be fair to Van Frazen, in his case, it does show up insofar as he emphasizes the importance of the scientific community. When he says, for example, that these science fiction cases of people with certain special eyes, they are not part of our epistemic community. The community is a reference point of the argument. That's one thing that came up. Another thing that came up, you said, why is it so human-centered? What is so special about the human observer? And you're quite right to emphasize this point, and that is indeed, it strikes me, that's the most fundamental motivation that drives all of Van Frazen's philosophy of science. That will become clearer, or would become clearer, if I had time to explain his criticism of structural realism. Van Frazen is trying to make as strong as he can the position that science makes sense only with reference to the human measuring system. That we cannot make sense of science as something which is thought of as separable from the nature of human cognition and the human body. That's what you recognize there as what you find a problematic feature. Von Frasen would say, you have perfectly well identified what ultimately motivates me. He is against the idea that we can think about science from a view from nowhere. He says we can only make sense of science as a human activity.
May I clarify? I mean it as well, like ontologically, right? Like in the sense that, okay, so I assume there's a world outside of me, there are people outside of me, so I can kind of do that. But I could formulate the same theory without needing this. I could say, okay, here's my mind, these are things I observe, these are ways to make assumptions about these things that I can observe. I don't need like anything outside, right? It's more like a practical view in this sense. So what I mean is like you don't need the human category in the sense of the body of the human person. You just need the mind in itself. Like, what can I know about the world? Doesn't have to be restricted to my physical being.
Well, that's precisely the point where Von Frasen would disagree. Von Frasen would say that ultimately all measurement refers back to the human body. Ultimately, the calibration of all instruments, if we lead back the chain of instruments, the human body is the final measurement instrument, with reference to which all others of our instruments ultimately have to be understood. So it's not just about the mind, it's also about the body. Yeah.
What kind of intersubjective, I wouldn't dare to say objective in the context of von Frasen, what kind of intersubjective elements are then there in von Frasen's ideas?
What kind of intersubjective elements are there? Well, certainly the observables for a given scientific community are intersubjectively there. So the kind of things that you can observe, measurement results that you can jointly measure with others. Additionally, medium-sized dry goods that you can talk about and identify with others. But it's sort of, or more generally, all the entities that in your scientific community and also in your everyday non-scientific community are assumed to exist. They exist as things that different observers can talk about and can identify. Yep.
What is the distinction between instruments and our senses?
Good.
So we know that we have optical illusions, are hardwired for, and we know that our perception is not evolved to be really precise, right?
Yes.
So,
very good point. So I don't know whether everyone heard the question. Did you hear the question? So the question was, how do we compare instruments to our senses? We know that our senses are often unreliable. We might also think of our senses as instruments. How do we conceive of that? That's indeed a tricky issue. And of course, one way one might respond to von Frasen is to say, well, you're so nervous about claiming that in instruments we see objects, but isn't our whole visual system an instrument? And we are using it precisely to make claims about objects. Okay, there it's important to von Frasen to really draw a line between the instruments that are part of our body, that make up our physical constitution, and other instruments. That's where he draws the line, and he thinks he can draw the line using the results of science, because science tells me what instruments are part of my physical body, and what instruments are potential additions to it, like microscopes and telescopes and my eyes. So there he thinks he can refer to science to draw a distinction. That's one. The other point, of course, it has to be admitted that our sensory apparatus is very unreliable in many domains and in many dimensions. But that doesn't change the fact that science also tells us that in certain dimensions and in certain respects, it is reliable. So there's kind of a circular relationship between our use of our senses and what science tells us about the reliability of our senses. We have found out by physiological and psychological research what are the circumstances under which, say, our eyes are not reliable. And then, of course, a careful scientist will not make observations under those conditions. But by the same token, we have found out under which circumstances our senses are reliable and can be checked by other observers that can possibly correct us. So
for example, we don't have the gravitational wave sensors in our bodies, right?
Right.
So we can just rely on instruments, on anything about those entities or those realities.
Well, by saying we can use instruments to find out about the unobservables, by saying that, you've simply committed yourself to scientific realism. So you haven't given an argument for it, you have just kind of said, I'm a scientific realist. Yeah?
So what about cyborgs? Augmented senses? You could in part it's even statistically possible. For instance, there were people who were blind and got implants that they could at least rudimentarily see. So would that count as a part of the body or as an extra instrument? It's kind of
right. I mean, we here need to speculate. We can only speculate what Van Frazen would say. I don't know whether anyone has put precisely that point to him. But I mean, let's start with a less high-tech version of it. Some people say, well, look, insofar as I'm using glasses, I am already using an instrument. To which Van Frazen's reply is, on that score, well, I can take the glasses off and get closer. So now I can see you clearly. If I take my glasses off, I can't. But if I come within 3 centimeters distance, I can see clearly again. So there is not bothered by this. So likewise, if you take the person of the blind, trying to do this by analogy, right, to using the argument about the epistemic community as the central argumentative tool here, is to say, well, it may be that blind people can only see in virtue of having a certain instrument implanted in their brain. But they are part of our epistemic community. And so we can sort of calibrate them against what we mean by seeing, in our case, who do not have that implant. And then maybe, insofar as we treat them as members of our epistemic community, we decide that in their case we shall say observation is what they are doing. We might also conclude by saying observation is not what they are doing. I guess that will very much depend on the nitty-gritty of how that mechanism actually works. Whether Van Frazen should be committed to us to say they see, they observe with the help of inferences drawn by the mechanism that they got, or that whether one should say they are not actually observing. So I don't think there is a clear-cut answer either.
Yeah, the problem with the community is that there's no reason why we couldn't eventually have entirely new senses by technology.
Well, to that, Van Frazen would say that's the answer he gives to Churchland. As our epistemic community stands now, we don't have that. Who knows, maybe in 10,000 years we have that, if we are still around. Then one needs to reconsider how we draw the boundaries of our epistemic community. So there are like two indices in Van Frazen's thinking. He makes it relative to the human body. He makes it relative to the epistemic community. And of course, third, he makes it relative to time and historical period. It might change. But as things stand now, he thinks we would draw the boundaries that he is drawing. So,
maybe it's my comment and a question, but going back to this idea of having a body of empirical knowledge here and theories there, it's not so separated in practice, right? And so we have examples, and Einstein is famously quoted saying, "Die Theorie entscheidet, was wir beobachten." The theory will tell us what we're going to observe. So it is in light of this, it's very tempting to have a scientific realist position by saying some people developed a theory and predicted something which we would have never been thinking about or speculated about, and if we had ever stumbled upon this observation, we might not have known what it means. Example, general relativity, where we now observe compact stars and maybe black holes, right? So it is not so easy to dismiss. Also, I guess the general consensus amongst physicists is that theories are evolving and there's no thing on sich we're going to find with physics. But it is very tempting if we see some examples in history where by theoretical improvements and new developments, we were really able to observe new things which we had not ever.
Yeah, I think your comment touches upon something that I have not yet much said about, and this is the theory-ladenness of observation. I mean, the famous example from Kuhn is when Aristotle sees a pendulum, he sees an object trying to find its natural place. When Galileo sees a pendulum, he sees an object continuing in an eternal motion. So by looking at the same physical object, they actually see different things in light of their theoretical commitments and in light of the theory that they have for describing the observation. That is, of course, a further complication, and it is, in fairness to van Fraasen, a complication that he is very well aware of. He does recognize that we sometimes use language for observation in which we seem to make commitments to unobservables. But he thinks, yeah, of course, we talk that way. But we should be reflective and think whether that talk really licenses a certain claim to existence.
That's true, but we would not have looked for light deflection if the theory wouldn't have said.
But that's fine. But that is something van Fraasen has no problem with. I mean, it's what I said earlier. He doesn't want to change the practice of science. It may very well be that our thinking about unobservables, about theoretical entities, has suggested new possibilities of observation to us. I mean, the van Fraasen scientist does everything that the scientific realist scientist does as well. He just doesn't make the ontological commitment.
I had to think about this Voyager spaceship, which was sent out some decades ago, carrying a plaquette with all sorts of messages from the human civilization. For instance, I think it was, among other things, the hydrogen spectrum. Yes. It was the direction to certain pulsars, etc. So, which we think that we are, so to say, communicating facts about nature and about, so to say, our position in the cosmos. And these facts should be recognized by any intelligent civilization, no matter what kind of eyes they have or whatever. Well, of course, this is a bit far-fetched because it's almost certain that this plaquette will never be found, but never from a philosophical standpoint, one might nevertheless ask the question, would van Fraasen say we are communicating facts about nature, or what are we doing with this enterprise?
Right. I think van Fraasen would say, or probably I would say, that if this was found by some other civilization, by some other life form, it is extremely unlikely that they would understand what they're being communicated. I mean, it reminds me of the idea that some people have about there's a philosophical literature that concerns itself with the question, how would we communicate with other civilization that we found somewhere in the universe? How would we communicate with them? Sorry?
Time numbers.
Well, and one answer is to say that, well, the way we would communicate with them is that every rational creature would speak the language of mathematics. So that, like, mathematics is not human-centered, as it were.
Send them the number pi in
Right.
digital form.
Yeah, okay. Yeah. I mean, this raises deep questions in the philosophy of mathematics that I cannot go into, but I want to at least point out that there are, of course, philosophies of mathematics which assume that mathematical truths are truths about things that are there anyway, whether they are humans or not, and that these kind of truths are such that every rational creature would have to grasp those truths in order to be rational. That's one view of mathematics. It's broadly speaking a Platonist view of mathematics. There is another view of mathematics which is goes back to the likes of Wittgenstein, who would think that mathematics, just like Van Fraasen thinks about physics, is something essentially tied to what kind of creatures we are, and that one cannot separate mathematics out from the kind of creatures we are. I mean, we can debate this until tomorrow morning, but I'm just saying it's not the only option to think about mathematics such that wherever we would encounter rational creatures in space, they would have to speak the language of our mathematics. That's far from without alternative language. That's all I can say like that.
So I found this idea that ultimately the ultimate instruments are part of our bodies very appealing. However, the step from this idea towards that Jupiter exists, but the electron does not exist, is highly non-trivial. So it seems to me that the reason why we can say that Jupiter exists is because we run into no problem with our observations with our bodies if we assume that. And the reason why it doesn't work with that is just the opposite. Because we do run into problems, assuming the existence of electrons, at least according to the mechanical description of it. And if the development of science would be different, we would find that actually the behavioral electron could be obtained through some hidden variables, through the existence of perhaps trajectory variables, then we would be believing in the existence, reality of this trajectory, although it would be based only on the traces in the vacuum channel. So it seems to me that there is another non-trivial element that one has to add into, well, our bodies are the ultimate instruments in order to decide what exists.
Right, and this further element you wanted to consider was do we run into problem by either assuming the existence or we don't assume the existence, right? Right. Now, I don't think Van Fraasen would particularly be bothered about this, because I think in the way you were setting it up, you were assuming that Van Fraasen must say that electrons don't exist. He's not saying Jupiter, moons of Jupiter exist, but the electron doesn't exist. He's saying we remain agnostic with respect to the question whether electrons exist, but in our theorizing in physics, in quantum mechanics, we can theorize with that entity. We just theorize with it in an as-if mode. We don't commit to the existence, but we make all the calculations that the scientific realist using quantum mechanics would make. So there isn't, I don't see the problem that one could run into such that a Van Fraasenite approach would end up having a problem that the scientific realist can solve, but van Fraasen cannot solve.
Why is reduction not possible in scientific realism? Like, because we say that there's scientific claims about theoretical entities, they cannot, like, reduction is not possible for them. But there, on the example, you have like heat as an example for reduction, and if I believe in it in a scientific theory, and therefore I believe in like electrons, why can I not use this kind of I don't know, reduce this further to something smaller or like?
Oh yeah. Okay, no. There's a misunderstanding. Of course, the scientific realist will accept that reduction in science often occurs. So no, that I didn't mean to say that a scientific realist never accepts reduction. What the scientific realist does not accept is that talk of theoretical entities can be reduced to talk of something else, not scientific, not theoretical entities. So in other words, talk of a theoretical entity like electron is not just shorthand for a very convoluted description of observables. Yeah.
Okay, yes.
Okay.
What exactly is meant by observing by van Fraasen? Because obviously there's the whole human cognition. So maybe you can see an electron, but if there's an electric charge, you can feel the electric field. So is that already inferring, or is it still observing the electron?
When you measure the electric charge,
yeah, you feel it.
You feel it on your body. Yeah. Well, I mean, there is something observable there. There is the electric charge that is observable, but it's still a step from feeling an electric charge to saying there is an entity of this or that kind that causes the electric discharge, right? That would be the inference, and that would be the step from going beyond the observable to a theoretical entity. Okay, I can't remember who was first. Gentleman back there.
I just wanted to understand better the relation that existence, let's say, as we are talking here now, is related to consciousness, for example. So, because I would say, for example, that a statement would be, for example, I do exist, something like that. That is very much related to consciousness. Why? When I speak of external objects such as Jupiter or electrons, then I don't have the same, let's say, concept of existence. No? Or is it totally equivalent? So this is what I don't understand.
Sorry, I don't understand your question.
So when I talk of existence of myself, for example, I intend something. So my conscious, I'm conscious that I exist.
Yes.
While when I say Jupiter exists, this also is not that I'm conscious that Jupiter exists, it's something different. So I wanted to understand better the relation between the two types. So one claim is that I'm conscious of my own existence, the other claim is that I'm conscious of an object that I cannot directly observe. That's the... the question would be more, what do I mean when I say Jupiter exists with respect to the existence of myself? Are them the same concept or are two different?
Okay. So you want to know whether like existence is univoque, has the same meaning everywhere, or whether for different type of entities we have different notions of existence.
Yes.
So you might think
how much this is related to human consciousness?
Yeah, I mean, I don't quite get the link to human consciousness, but of course we can talk about existence of different types of entities in different ways. So even say if a Platonist says that numbers exist, existence need not mean the same thing as when I say this or that physical object exists. And of course, philosophical work in metaphysics and ontology is about trying determine whether it's the same concept of existence or it's not the same concept of existence. Just not so, I don't quite see the relevance of that concern with respect to the things we have been talking about.
Yeah, because for example, I don't need a measurement to know that I exist, for example. Why? To know that electron exists or Jupiter exists, then I need some instrument.
Right, yeah. But that's von Frasen's point. To determine the existence of some things, like do I exist, I do not need any kind of instruments. Or if I make claims about things that I see in my immediate environment in broad daylight, for that I do not need instrument or any help of any kind. But there are other circumstances of observation where instruments are involved. Just don't see the. Well, maybe we should return to it afterwards. There was a question here. Maybe the gentleman first.
I'm wondering what difference does it make if I'm a realist scientist or a constructivist. First you told me there is no difference in the scientific practice. The only difference I can think of is if my pet theory or my favorite theory or my theory is abandoned or gets abandoned. If I'm a realist, I will fight to my death to anybody who wants to make it abandoned, because everything is real and therefore I cannot accept it. If I'm a constructivist, I say, okay, bad luck for me, never mind.
Okay. That's a misunderstanding. First of all, let's look at the scientific realist side. The claim is not that scientific realists must think that their theories are in all respect true. I mean, they can reduce the scientific realism a bit without having to give up anything of its substance. So they might say that their theory are approximatively true. So it doesn't mean that they're true in every respect. So even the scientific realist can accept that, of course, my theory may have to give way to a better theory, but he will then say, well, the previous theory at least approximates the latter theory. And the theoretical entities that are postulated in the successor theory will preserve essential features of the theoretical entities in the previous theory. So a scientific realist is not someone who thinks, I found the truth once and for all and I don't have to move. So it seems to me a scientific realist could be modest and willing to change their theory. On the other hand, the constructive empiricist could also be dogmatic. So dogmaticism, humility don't seem to me to map on very nicely on that distinction. Von Frasen, of course, will insist that his position has the greater degree of humility. In a later book of 2002, von Frasen makes a distinction between two stances, zwei Haltungen, two stances that one might have when it comes to science. One stance is the empirical stance, and that's the stance of modesty. We don't assume that our theories make true claims about unobservables. We don't assume that we can have knowledge of unobservables. That's the position of humility. And he thinks that the scientific realist has a position, the position of this metaphysical element that is central to scientific realism, that von Frasen finds immodest. So there's a difference there. But you started off by saying something which reminded me of the introduction by Professor Bruckner, which was the idea, so does philosophy make any difference whatsoever? Like you were like saying, isn't it the same which of the two I adopt if I'm a scientist? And the answer to that question has several dimensions. One is to say, well, of course, you don't need to ask philosophical questions. So you can do your science successfully all your life without ever raising a big philosophical issue. If one doesn't if one doesn't feel the force of the philosophical concerns, then one can perfectly well work without them. So philosophy only becomes a problem either when you don't know how to carry on with your science and you kind of hope philosophy will help you out, or you simply get pushed to ask sort of questions that would not arise in your ordinary philosophical work, which kind of takes me back to that comment by who was it again? Feynman, that like he could like take Spinoza's ethics and negate every key claim, and that would also be possible. Well, that betrays, I think, a rather simplistic understanding of philosophy, because what he says is true. It is indeed the case that very often when one does philosophy, one ends up having two or more theories, and one can't clearly decide between them. So is the scientific realist view right? Is the constructive empiricist view right? Is there maybe a third or a fourth alternative? And then the naive view is to think, well, if I can't clearly decide between them, why should I care? But sometimes progress in thought consists not in finding out which theory is right, but in trying to find out what are the possible options, what is the scope of views from amongst which it is likely one of them is the correct view. Very often progress in understanding is precisely that. And it seems to me that progress in philosophy almost always is of that nature. Because take all the big philosophical debates, freedom of the will, what have you. Progress in philosophy has been understanding better what the different options are, rather than being able once and for all to kill off one of the views. And since I'm having this rant against Feynman, I want to criticize the view also from another position. This view, like to say, philosophy, do we need it? Isn't kind of philosophy a waste of time? Reminds me a bit of the debates I have with my pubertarian daughters about whether classical music is worth listening to. Because the way I'm arguing against them is to say, well, give me any feature of classical music that you think makes it worth not listening to. And then whatever feature they give me, I can give them some non-classical music which has that feature, and I can give them classical music which doesn't have that feature. Classical music, in other words, what I want to say, classical music is so vast that to say, I don't like classical music is saying something completely meaningless. Likewise, I want to say, and now I'm comparing Feynman to my pubertarian daughters, when Feynman says philosophy is a waste of time, or Hawking or other famous scientists make this view, they remind me of my pubertarian daughters. Because philosophy is so vast that to say philosophy, period, is a waste of time, that just shows that you have a very thin and simple diet of philosophical nourishment on the basis of which you are making that claim. Thank you for the applause. So the idea is that I now move to structural realism. Yeah? Okay. Okay, so I will try to compress it into about maybe 25-30 minutes so that there's a little bit of time for discussion. So structural realism. This is an idea that so far the classical scientific realism always talks about theoretical entities. We talk about electrons, we talk about genes, we talk about black holes. But over the last 20 years or so, philosophers of science have said, no, look, scientific theories, also the unobservables, are much more complicated things. So when we have a scientific theories, we have some sentences that concern observable entities, like black holes, genes, electrons. But the scientific theory also, and of course, talks about certain theoretical entities that we cannot directly observe. But there are also claims made about structures about mathematical structures, about formal features that cannot be reduced to just to talk about entities. And that if we want to defend a plausible form of realism, we should not so much focus on the entities, but we should focus on the structures. This also involves a claim about scientific progress. I mean, the scientific realists are often come under pressure from the argument, the pessimistic meta-induction, that entities that were once deemed important, like the crystal spheres, like the humors, like phlogiston, that in the progress of science, such entities were later thrown out. That's a problem for the scientific realist. And scientific realists feel the force of this argument. But they still want to retain the idea that there is a genuine sense of approximation in the sequence of scientific theories. Only what they now want to say is that the approximation is not we get ever closer to the right theoretical entities, but in more recent forms of scientific realism want to say we get ever closer to the right structures, to the relations that might exist between entities rather than these entities themselves. So here this picture, I've tried to capture this. Again, the ball is a scientific theory. So we have sentences about observables, and then we have sentences about unobservables. If we then move to the successor theory, what we typically find is that the things the previous theory talked about, the theoretical entity things that the previous theory talked about, they are often given up. But what is retained are the structures that the previous theory identified. Perhaps the best way to make this clear is to take the most important example that has been discussed and introduced by the London-based philosopher John Worrell, who claims that structural scientific realism is the best of both worlds, meaning we can stick to the central ideas of scientific realism, but at the same time we can also do justice to the pessimistic meta-induction. So his example is the theory of light in Fresnel and Maxwell, and the important feature of that comparison between those two theories of light is that for Fresnel, light consisted of vibrations or waves transferred in the ether. That's what Fresnel said. Maxwell says light consists of vibrations, waves in the electromagnetic field. What vibrates are electric and magnetic field strengths. If we look at this case, Worrell says, what we notice is that there is no continuity of entities here. Fresnel talks about the ether, and Maxwell says there is no ether. So on the face of it, this looks like what Van Fraasen, or the critic of scientific realism, would want to take comfort from. The entity is not preserved. But, says Worrell, if we look at this case, we note that despite the fact that Fresnel talks about the ether and Maxwell doesn't talk about the ether, there is a deep continuity here. Namely that the mathematical equations that Fresnel formulates for the vibrations of the ether are kept by Maxwell in order to describe the vibrations of the magnetic field. So there's a continuity of structure here, even though there isn't a continuity of entities. And so we should apply the inference to the best explanation, not to particular entities, but we should say what accumulates in science and what we get ever closer to are structures that are captured by our mathematical apparatus. This basic idea of structural realism can then be further developed in two different ways, corresponding to the epistemic ontological distinction that we already played with earlier. For example, when I said that there are two kinds of skepticism, epistemic and ontological. Here we have two forms of structural realism, one epistemic, the other ontological. The epistemic structural realism says, well, we should only believe what our best scientific theories tell us about the relations between unobservable entities. Don't believe in the unobservable entities. Just believes in the relations between them, because that's the form, that's the thing that our mathematical machinery captures. Only believe in that. So it's kind of epistemic because it tells us what we should believe. Whereas ontological realism, so epistemic realism doesn't deny that there may also be theoretical entities. It just says, well, those we can't really get clear of. They might change from one theory to the next. What we can be clear about is the form, the relations between the entities. The ontic structural realism is more radical. Ontic structural realism says there are only relations. There are no nodes to those relations. This is a claim that James Levyman and Don Ross explain in a book entitled Everything Must Go. And they don't mean everything must go, but everything must go, which is to say that the only thing that actually exists is structures. And we should get rid of the old-fashioned idea that there are entities. It is as if, if you have a network of relations, don't think that the nodes actually are things. Get rid of that idea. And they claim that if you properly understand the lessons of quantum mechanics, then this is precisely what you should take away from it. The details of that you really have to read up in their book. I'm not enough of an expert on quantum mechanics to be able to explain why they think that quantum mechanics best underwrites this view. Okay, now this view has been criticized from various directions. One criticism comes from Stathis Psilos, a classical scientific realist, and he says, well, what this view overlooks is that the nature and the structure of a physical entity forms a continuum. We cannot neatly subdivide scientific theories by saying this is part of the structure and this is part of the inventory of entities. In reality, these things are far too much intermeshed for us to be able to believe the one and not believe the other. That just doesn't work. And of course, they point out that this case of the Fresnel-Maxwell relation is one example, and it's not at all clear that scientific progress in general can be captured by saying the mathematical apparatus states, or the earlier mathematical apparatus is like just a special case of the later mathematical apparatus. Sometimes maybe, sometimes not. One would really have to look at a very wide range of scientific examples. It's also, of course, quite a radical metaphysical view to say there are no entities. One has to do a lot of philosophical work to make that plausible. It's also not unclear whether it maybe just works for quantum mechanics, but not clearly works for anything else. There's uncertainty about that. And there's also the concern is whether it doesn't conflate mathematics and physics. It may be that a certain mathematical apparatus stays from one theory to the next. But why should we assume that the mathematical apparatus that stays from one theory to the next kind of is an ultimate truth about the physical reality? There may be all sorts of pragmatic, practical reasons why we keep the same mathematical apparatus. And it's a big jump to say this mathematical apparatus best helps us to make predictions, and to go from that to the further claim, in reality there exist structures that this mathematical apparatus actually describes. That's a big jump. I mean, that's a jump from the mathematics to metaphysics, or from mathematics to physics. Just because a certain form of mathematics is particularly apt for use with a successful theory is one thing. To say that this mathematical apparatus mirrors or approximates structures that really exist out there in the world is quite something else. And there's unease about that move that the structural realist wants to make. Okay, but again, I want to give you the Van Fraasen alternative to structural scientific realism. So in his book, he's still climbing mountains, in his book, Scientific Representation of 2008, Van Fraasen says, there is something importantly correct about this structuralist move. I agree with it. We should indeed pay attention to structures. But we should not draw these kind of conclusions that the realists want to draw from it. And I want to explain to you quickly how he does that. Well, the first element of his view is that he says we need to really understand what representations are. So when we say that scientific theories represent the world, we need to understand the concept of representation. And it's interesting that although the concept of I'm sorry, that's my daughter. She wants to discuss classical music, but not now. We need to make sense of the talk that scientific theories represent. And to make this clear, he first of all draws the distinction between phenomena and appearances. Phenomena are things that we can observe. Phenomena are real things out there. Appearances are the contents of observation. So when I see something, the content of my seeing is a phenomenon. Or when I make a measurement, what I see in my measurement apparatus, that's a phenomenon. And he says we need to understand representation as a certain relationship between phenomena, that is an appearance, I should have said in the last sentence. We need to understand the relationship between phenomena and appearances such that appearances represent phenomena. So what then is representation? Well, there is a naive view of representation which says A represents B when A is similar to B. This is a view that has been much criticized, and Van Fraasen agrees with the criticism and says, yeah, one problem with this view of representation is similarity, is that representation has an asymmetry that similarity doesn't. If A resembles B, then B resembles A. That goes in both directions. But if A is a representation of B, B is a representation of A. If I draw the face of Flavio, that's a representation. My picture represents his face, but his face doesn't represent the picture I draw. So representation has an asymmetry which similarity lacks. And Van Fraasen says, yeah, that's true, this general criticism is correct, and what breaks the symmetry in the case of representation is the context. It's the context that decides which way the similarity works. And quite in general, he says, in order to understand representation, we need to pay attention to context, and we need to understand that representations are always made by a human for a certain purpose to address other humans. So the right formula for understanding representation is the formula person or scientific community Z uses X in order to represent Y as F. To repeat, representation is Z uses X in order to represent Y as F. The important element is that representation always has someone with a certain intention. We have a certain object that is being represented, but it is represented in a certain way for a certain purpose. When we here in this formula say use, that uses X in order to represent Y as F, he says this use covers many different things. For example, the intentions of the producer, or the community's conventions, or the way in which there's a social element there. The gentleman was earlier asking after that. The ways in which the observer grasps the phenomenon, or the way in which the object is represented. So use has to do with intentional human action of trying to influence other people in a certain way. And he wants to say these general features of representation, which initially he works out in the case of works of art. He says one of the best ways to understand what representation is to look at pictorial representation in art. Because in that case, we have had 300 years of theorizing about what a representation is. And we can abstract from those debates in the history of art a general model to think about representation, which we then can also apply, mutatis mutandis, to scientific representation. And that's what he's doing. So these kind of features are abstracted from pictorial representation in art, but then he says, well, interestingly enough, these same features we also find in science. Remember, he also, this is the important point, we touched upon this before, this essential human-centeredness of his view of science. So when we talk about representation in science, we are not talking about the relationship between an equation and the world. We are not talking about the relationship between a scientific model and a real system. But to understand representation, we always have to put into the equation, if I can use that word in this context, we have to put in that the model is used to represent something for an audience by an actor, by a human actor. So representation has irreducibly the element of something is done for a certain purpose by a certain human actor. So he says, well, the same also applies to mathematical representation. Mathematical representation is also interested and human-focused as well. He says, well, think of a beer glass on a table. We can use different geometries for representing its form and boundaries. Okay. Another important distinction that he introduces, or the concept that he uses in the context of explaining representation, is indexicality. This is the idea that if you think about perspectival painting or perspective in painting, it always paints the picture so that you have to look at the picture from a certain direction, from a certain angle. The picture kind of contains the advice of how you have to look at it appropriately. So the picture has an essential indexicality, an essential advice on how you have to situate with respect to the picture. So a picture gives you the advice, this is how it looks from here. Here is an indexical term. Indexical terms are terms that shift with context. When I say I refer to this person, Martin Kusch. If one of you says I, it refers to them. That's an indexical. So it shifts with whoever happens to be speaking. Same with here. Here is where I am. Here for you in the back is there in the back. Again, it shifts. So representation for him is essentially indexical. Representation is always from a certain position of a certain human with respect to certain others. And he says the Cartesian idea is, of course, to have a coordinate system which is not perspectival, which is like a view from nowhere. That's like the Cartesian idea of science, of having a form of representation that leaves behind the humanness, the human focus. And he says, well, that may be good as far as it goes, but even with respect to the Cartesian model, once you want to apply the information that is encoded in a Cartesian idea of a coordinate system, the moment you want to apply it, you need to know where you are relative to that coordinate system. So even the Cartesian ideal is not free of indexicality. The moment you apply it, you need to put the index in where you are relative to the other objects in that space. He puts it as follows, a very key quote from the later position. The body of pure fundamental science can in principle be written in coordinate-free, context-independent form. But to draw on this body of science in technology, the scientist or the scientific community must supply something extra, which does not come with that body of science, but serves to locate the user with respect to it. And all these are arguments, and all these are descriptions meant to make clear that scientific representation is representation that is relative to the human perspective. Okay, I have to speed up a bit. So let me just say a couple of comments about measurement. He's trying to say the same thing about measurements. And the key problem of measurements is what's often called in philosophy of science the problem of coordination. Let me introduce this with this picture. Let's say we are trying to introduce a thermometer. Well, when we are trying to introduce a thermometer, we are trying to relate different states of the object we are trying to measure with different states of our measurement instruments. Right? That's what it means to calibrate a thermometer. We relate states of the thermometer, the height of the mercury column, for example, related to different states of the object. Now, how can we do that without already knowing and being able to distinguish the different states of the object? Right? We need already to be able to identify. We need already to be able to identify the different states, the different temperature states, in order to be able to say, okay, this temperature state should go with this height of the column. This temperature state should go with that height of the column. Well, in order to be able to do this, we need to be able to tell apart these temperature states. But how can we do that without already having the thermometer that allows us to tell those states apart? Do you see the problem? No. Let me try again. The difficulty is, assume that we were the first people to introduce a thermometer. Assume we haven't got a previous type of thermometer to fall back on. It's the very first introduction of the thermometer. We are trying to relate different temperature states with different heights of the column. Forget about all scientific theories we might have or anything in the background. We're just trying to relate, to link up different states, different temperature states of, say, the water that we are trying, temperature of which we are trying to determine, and different heights in the mercury column. Well, the difficulty is how can we distinguish between those states appropriately in order to match them to those different mercury columns. Let me just finish the explanation. Van Fraasen says, well, that might work, of course, if we already have a scientific theory that governs both of the temperature states in the water and that also cover the height of the mercury columns. Then, of course, it is possible. It might also be possible if we have a previous generation of thermometers. So assume that, for example, we have a thermometer, before people had mercury thermometers, they had water column thermometers. Well, maybe we can use the water column thermometer in order to calibrate the mercury columns thermometer. But his point is that when we go back and then ask, well, how can we introduce the water column thermometer, there comes a point where we have to go back to sticking our fingers into the water and to distinguish between different temperature states on this side using our own body as the ultimate measurement instrument. That's the key idea this leads up to. That measurements, when you go back the sequence of instruments and how they were introduced, ultimately we are forced to go back to discriminations that we can do with our own body. This is meant to highlight the ultimate human-centeredness of measurement. Even though measurement has developed far and wide beyond anything to do with our body. Of course, he's not for one moment denying that. Of course, we can do things that we could never do with our body now. That's true. But the point is that ultimately, if you go back the chains of instruments, ultimately, you fall back on the human body as the first instrument. Okay, and maybe that's the bit I leave there. Maybe one other bit I want to explain, but I jump straight to the key point. And this is this picture, because I want to explain in what sense his structuralism differs from the scientific realist structuralism. So this is basically van Frasen's more recent view of science. Let me take you through the different elements. The first element is that we have phenomena out there in the world. Remember the phenomena appearance distinction that I mentioned. Phenomena are things in the world. Appearances is how the things in the world appear in our observations and how they appear in our measurement instruments. That takes us here. Then, of course, we don't stop there. When we have our data from our measurement instruments, we make data models out of them, more abstract representations of the measurements. And of course, we go further from more simple-minded data models to more abstract mathematical representations of the data. That's the normal progress in science. If you want to have a very simplistic picture that I can explain in 1 minute, assume I wanted to have a model about the heights of the students in my lecture. So this is supposed to be the students in my lecture. Assume there are 20 of them. I can first draw a histogram. There are 2 students that are 140 centimeters, and then there are 4 between 140 and 150, and so on. In the next step, I can make a data model out of this by giving a distribution of relative frequencies. And then, of course, I can come up with a function that describes the data. Call this the surface model. And then, of course, what might happen is I might want to be able to test that surface model, use it to test my theory about heights of humans. So assume that for van Frasen, a theory is a set of models. So assume that I have a theory about human heights, about what kind of nutrition people have and how likely they are to reach a certain distribution of heights. So assume I had this theory about Viennese students, of course simplifying a lot. So I have a theory about the average height about Viennese students, not now built on my data, but built about general assumptions about nutrition, about the amount of sunlight one gets when one lives in Vienna, and so on and so forth. And so that theory, say, predicts this kind of line. So I have a theoretical model which tells me, well, if you draw a population of Viennese students, and that's what you should see. That's the theoretical model. Okay, well, if I'm lucky, then the theoretical model and the surface model are isomorphic. Now, that's the key elements of van Frasen's own empiricist structuralism. Namely, he says, the best you can get in science is that you have surface models that can be isomorphic to theoretical models. We have here a coincidence of 2 structures. So his structuralism is a structuralism that tells us what counts as ultimate success in science. Namely, that you have a data model or surface model that can be isomorphic to a theoretical model. But, he says, what he's describing there is not anything that exists in reality. The claim is not that reality has a certain mathematical structure. The claim is what he's describing is what counts as success in the practice of science. He's describing the practice of science, not some ultimate features of reality. There's a good formulation of it. Yes, his form of structuralism is not a view about the nature of reality, but a view about the nature of science. The claim is not that reality consists of mathematical structures, and if we have a successful theory about nutrition, then we have captured the mathematical structure of reality. That's not the claim. The claim is it's the nature of science to aim for isomorphisms between theoretical models and surface models. Let me go back, which brings me back to this picture. On a naive view, you might think, well, isn't that some kind of correspondence here? Isn't it that like the theoretical model corresponds to the mathematical model? And isn't this isomorphism a bit like maybe to be taken like the correspondence theory of truth? That if we have an isomorphism here, shouldn't we then say that the theoretical model is true of the way the world is? Von Frasen said we should be cautious about saying that. Why should we be cautious about saying that? He says we should be cautious about saying that because if we do say that, we overlook that the way we make the phenomena appear and the way we construct our data model, that is essentially perspectival. We choose a certain way to represent the world. And representation is a person presents something in a certain way to achieve a certain effect on a certain audience. So there is a match. But whereas the scientific realist would want to read this match as correspondence between the theory and the world, the constructive empiricist says, yes, there is a match, but the match is between our theoretical models that we have made and our surface models. And the surface models are something that we have made from a certain perspective. So structuralism is all right if it means that representation in science, especially natural science, is almost always mathematical and involves isomorphism of surface model and mathematical models. That's the structuralism that is there. But this is a structuralism about the way science is conducted. It is not a structuralism that entitles us to believe that reality has certain mathematical properties. So you see again how von Frasen differs from the scientific realist. The structured scientific realist wants to make claims about our best scientific theories, even in their unobservable parts, tell us what the world is like. Von Frasen wants to say, well, focus on the things that are observable. What is observable is that a certain surface model is isomorphic to a certain mathematical model. There are two lines, and we can see whether they match. That's observable. It's also the case that phenomena are observable. It's also observable. But in between here, in the way we construct our surface models, and of course the way we construct our theoretical models, our perspective and our interests and the way we are trying to convince others become part of the story. And when they become part of the story, claims about, and this is the way the world really is like, become dubious. Okay, that's all I wanted to say. We've got some time for questions, so. Okay, maybe we should have 15 minutes discussion and then finish so it doesn't get too late. Okay.
Sorry, you have not defined what you mean with surface model. So if I, from a physicist perspective, can I say you mean like fitting models of data? You fit the data, you get maybe some functional representation.
Yeah.
But that doesn't mean you have a physical theory which explains why you get this functional form rather than another functional form. That's the theoretical model, right?
Yes.
As opposed to that surface model which is a fitting model. Is that what you basically?
I mean, the difference is that the surface model is a way of representing the data. The theoretical model is a prediction of the theory on what kind of distribution of heights one would have to expect given the nutrition and given the sunlight and given the wealth of Viennese students.
That's right. But also with regard to the surface model, I mean, statistics has a whole body of knowledge to tell us what sense it makes to choose this functional form over another, say. So, and yet we may not have the theoretical model yet, or don't have it, to explain it, so to speak, more fundamental or more first principle, what that surface model actually means.
Right.
So can one say it this way, in a sense, even so Van Frazen might mean it in a more abstract, in a more metaphysical way? I'm just talking more like a physicist.
No, Van Frazen certainly does not mean it in a metaphysical way. The surface model is a way of representing the data, and of course statistics and all of this is all part of how you represent the data. But statistics is no view from nowhere. I mean, the way you construct your surface model, what kind of way of representing the data you choose is not something that's fixed in the sky, but that's a choice that you as a scientist make.
That's right, but science statistics as a science still has its own criteria how to choose it. It's not just a mere...
Of course, but it's not as if statistics is like a ready-made machine and it tells you, give me your data, and we tell you exactly how the data is to be represented.
No, and it's evolving. It's self-evolving.
It is evolving, and it leaves you choices as you do the representation. And that's all that Van Frazen needs.
That's right, and sorry, just related to this, now with all this big data coming up, there are people saying, well, maybe that's the end of theory, because now we're going to model all the data and machine learning, everything, and maybe we will just stay on the surface model level if we forget about the modeling.
Yes.
And so
that would still fit with, I mean, I don't think Van Frazen would have a problem with that. That would just mean that we kind of give up the idea that we need theoretical models over and above the mathematical abstract surface models.
That would be bad, in my opinion, but I'm saying there's maybe some trend.
Yeah, but from Van Frazen's point of view, that would just confirm that structuralism is right insofar as mathematics is essential to the representation in science. That's all the structuralism we have. If we give up even striving for an isomorphism between theoretical models and surface models, if we say surface models is all the theoretical models we need, that of course is in a way not good news for the scientific realist, because the scientific realist wanted something that justifies the assumptions made in the theoretical models. There was someone, you first.
Okay, so I think the main problem, and if I may make a joke as well, I think there's a hidden variable in the whole theory, which you kind of skipped in the beginning, and maybe that basically all of these theories assume there is a world outside of us. So like, solipsism isn't really a thing. And I think this is very important because like in this moment when this becomes a question which I can't decide, then it doesn't matter if this reality is, if my description of the reality is real or not, because I don't even know if reality is real. So it kind of boils down to this, and I think this was where we all found this kind of strange thing where you say, oh yeah, human things are different than other things. Well, where I would say, well, like, I don't know even if reality is real or everyone is just me, I don't know.
Right.
So, but I assume it, and I find the best description of it, but it doesn't, I don't know what's real anyway. So like in the sense that to think about, oh, I have this theory which describes it, like for me, a theoretical and a real object are the same thing. It's somewhat of a description of the world which I can get. and then like objectively assuming that this is true or real or something is a question I don't even try to answer.
Right. No, you're certainly right. You're certainly right to say that every philosophical debate starts from certain things that are being thought over and certain things that are being held in the background and taken for granted. And certainly this whole debate takes for granted the assumption that there is a world beyond our own thinking. And this is a world that we are trying to interact with and learn something from. If you say that I'm not going to share that assumption, I'm going to be a solipsist, I'm going to be an idealist, perhaps would be the more appropriate thing to say. I'm going to be a radical idealist and solipsist together. And none of these arguments touch me. You're right. But there are other philosophical debates that target that. I did not present an argument for and against solipsism. That just wasn't part of the debate we looked at. But you're certainly right. There are other debates. There are other contexts for which one wants to take that position very seriously. I mean, take other positions. Take epistemic skepticism, which says that we cannot know anything about the external world. Again, we haven't talked about epistemic skepticism. That was background rather than something that was at issue here. So yeah, you're right, but it's a different debate that you want to have than the one that these people are having.
One sentence.
Yeah.
But this doesn't exclude me from actually partaking in this reality and formulating a way of like constructing reality. I'm not saying like, oh, there is no, I don't know if there's a reality, so I just die. That's not what I mean. What I mean is like, maybe I don't need this differentiation between real or not real. I can still make a practical point of view, and I think that's actually what we do in physics quite often.
Maybe not. There would be lots to say about the sort of position you're sketching, but it would take us so far away from the discussion we've had here that I think we better set it aside. There was some question, yeah.
Well, I really try to stick to a question and not a comment.
Right.
When you were using many times in your talk the word form, you were referring to our understanding of this terminus as eidos, as what you understand in philosophical understanding of the word form, or you were just using the word form as we understand it in a very casual, daily way. And just a very short question again to that you mentioned that the success of science is just that we have a surface model that completely fits to the theoretical model that we have. So if we are trying somehow, under any circumstances, to find superposition of these two both together, so what's the point of science? So what is science?
Well,
because we are talking about the success of something which we have no idea.
Well, I mean, first of all, this talk about forms. This was meant to be gesturing in general towards structures, right? So we are the structure science realist says we're interested in structures, not entities. And there were times when I've used the word form just to refer to structures. The second question was, then what is science? Well, von Frasen tries to give us a description about what science is, and he says it is the nature of science trying to find mathematical representations of our data and as part of our theories that allow us to find such isomorphisms. That is what counts as success in science. So if you ask me what is science, the answer is that is science.
The term of being successful in doing that thing is science to von Frasen.
When we manage in science to develop appearances, find appropriate data models that our scientific community finds convincing, and if we succeed in in finding appropriate, more abstract mathematical representations, and we find them to be isomorphic to our theoretical models, that is what counts as success in science. Last question. Sorry. One here and one there, and then we finish. So you first.
As far as I understand, the Van Fraasen's theory is not a normative theory, as you explicitly wrote it in your slides and said it on the video. And so, on the other hand, the scientific realism is a normative theory.
A normative.
Yes. And so my question is, why should its physicists care about Van Fraasen's theory?
Right.
Because it's not a...
No, I think you are wrong about thinking that scientific realism is normative and Van Fraasen is merely descriptive. I think both are descriptive and normative, are meant to be descriptive and normative. I mean, the scientific realist, for example, wants us to accept that our best science is conducted such that it involves inferences to the best explanation, from which the scientific realist then draws the conclusion that that also should be the guideline for how we as philosophers interpret what science does. I mean, the same for Van Fraasen. Van Fraasen thinks that the aim of science is empirical adequacy and not truth. And he thinks that if we study science, we recognize that that's the goal of science. That's the descriptive part. But he also wants to draw the conclusion that therefore it's rational to stick to the constructive empiricist position. Another way of putting it is the following way. I mean, Thomas Kuhn, famous philosopher of science, who gives a description of the history of science, was sometimes asked, well, isn't that merely descriptive rather than normative? To which his answer was, well, I give you the description of our best science. And if I give you a description of our best science, that's also normative, because it's the best science. And I think both of those positions would say, we are giving you a description of how best to render and understand scientific practice. And therefore that's descriptive, but it's also normative. So it doesn't divide up the way you wanted it to divide up. So, last question.
In the sense of the pessimistic meta-induction, that it said that there were theories in the past and they are successful, but then given up because we concluded that they are ultimately wrong. Mm-hmm. So I have a problem with ultimately. How can you conclude that the theory is ultimately wrong?
Also, so this ultimately wasn't meant to mean that it couldn't happen in the future that this theory was kind of rediscovered and found to be stronger than it initially looked like. I mean, the way some people claim that, Feyerabend used to claim that central features of Aristotelian physics have actually returned in modern physics. I'm not sure whether that claim is true or false, but it's not meant to say that this couldn't happen. That could happen. So this ultimately was not meant to mean once and for all and we could never go back. It was only meant to be, from a later perspective, it turned out to be, we judged on a later perspective that these entities of that theory didn't exist. Yeah. Okay, we leave it here. Thank you very much.